Hi everybody. In this video, I'm going to explain the implementation and the result analysis of this project. So implementation, we have implemented all the attacks in Contiki Cooja simulator. But every attack in a different way. We cannot do the same thing for all the attacks. So we implemented every attack in a different way. Okay, for example, let me go for the black hole attack. So as far as black hole attack is concerned, for the black hole attack, so we use the file. The name of the file is uip6.c. So this is the file which is available inside this folder. So Contiki core net IPv6. Okay, this is the folder. So inside the folder we have the file which is uipv6.c. So this file, okay, we modify. Okay, what is this file is doing means, so this is receiving the packet and then sending the packet. Okay, so in this file we changed the code. Okay, the code is changed to, so not forwarding the packets. So any packet it comes, simply it is going to drop the packet. So this is the change we have done. Okay, for example, this is the sync node and this is the user node, UDP sender and UDP sender. So the UDP sender is created by using this particular file. Okay, C program. Now in the C program we modified whatever the packet comes from the neighbors, so automatically the packet should be dropped. So we implemented like this. So this is as far as the black hole attack is concerned. Now if you see the rank attack, for implementing the rank attack we change the file rpl private.h. This is a header file. So this header file consists of the information regarding the rank of a node. For example, if you take, this is a sync node, this is a UDP sender node, and this is the UDP sender. Now, the rank of this node is 0. It will be 0. The rank of this node is 1 and the rank of this node is 2. Okay, now if this node is going to be an attack, it is going to do a decreased rank attack means, so this node can change its rank as 1. Okay, this is a decreased rank attack. It is going to decrease the rank of, okay, of the particular node automatically. So now this is going to be a malicious node. Actually my rank is 2. I'm going to decrease my rank, okay, by 1. So why we are reducing means, if you see the next node will think, okay, the rank of the next node is 3. They will think that I am 1. Okay, I am the 1. Okay, so they will forward all the packets to me. But actually I am 2. Okay, so this is called the rank attack. So how we can implement the rank attack means, so the file which is available in the Contiki core net RPL. So RPL is a routing protocol. Inside this we have the header file. So in the header file we change the timer. Okay, timer.c. Okay, these two files we changed and we are implementing the decreased rank attack. Now the third one is a DODAG attack. So what is a DODAG attack means? So DODAG means the entire structure. Okay, for example, so this is a DODAG. Okay, so this is your sync. Then we have the sender nodes. Okay, many senders will be available. So this is called a DODAG. The complete name for this is a DODAG. You must know what is DODAG stands for. Okay, DODAG stands for. Okay, you must know. Now this is called the DODAG. Now what is DODAG attack means? So the DODAG attack is the every DODAG, okay, will have a number that is called the version number. Okay, version number. Okay, for example, if you run the topology now, so the version number will be 1. Then if somebody is joining, okay, if somebody is joining the network means now the DODAG is changing. Now the version is going to be 2. Again, after few minutes, somebody else is going to join. Okay, somebody else is going to join means then the DODAG version is equal to 3. So this is called the DODAG version. Okay, now what is DODAG version attack means? So in the DODAG attack, okay, this number will be changed by some nodes. Okay, so the malicious attacker, so suppose this person is a malicious person means, so this person is going to change the version of the DODAG. Okay, for example, current version is 3 means, so this person is going to do as 2. So or you can reduce it to 1. So this is called the DODAG version attack. So this how we implemented means This is the file. Okay, that means in the Contiki core net RPL. So this is the directory. Inside the RPL directory, we have RPL ICMP6. So this file, okay, we are changing, we are converting. So inside this, we reduce the DODAG version. Okay, so this is how we implemented the DODAG attack. Then the third one, then the next one is a flooding attack. So in the flooding attack, so the packet, that means the sender. Okay, for example, you can say this is the sync. Okay, the sync node, and we have the UDP sender nodes. So we have many UDP sender nodes. Now, what is flooding attack means? So for example, I'm going to take this as a, I'm going to take this node, I'm going to take it as a malicious node. Now, so this person already joined in the DODAG. Okay, he already joined in the network. Now, but what he will do means he will send again the request. Already he joined, already is available in the network, but he is going to send the packet. Okay, I want to join the network. Okay, so which packet is going to send means it is called the DAS packet. So the DAS packet is used for joining a network. So he already joined, but what he is going to do is keep on sending the DAS packet. Okay, in the regular interval is going to send the DAS packet. So this person is going to accept it and he is going to allow him to join, but already he has joined. So this attack is called the flooding attack. So this is called a denial of service attack. So how we can implement this means we implement it by changing the file rpl private.header. Okay, so rpl private.h. So this is the name of the file which is available inside this folder, Contiki core net rpl. So inside the folder we have this particular file, and in this file we created a loop. Okay, we created a for loop and we send the packet, the DAS packet, we send continuously. So this is how we implemented the flooding attack. Then the next attack is a selective forwarding attack. So what is selective forwarding attack means? In selective forwarding attack, there are two different types available, but I will compare selective forwarding attack with black hole. Okay, with a black hole attack. In black hole attack, okay, we'll go for an example now. See. So this is the root, or we can say it is a sink. So this is a user node, UDP sender, UDP sender. Okay, so we have the UDP senders like this. Now, I'll explain the black hole first. Okay, then I will go for the selective forwarding. Now, what is a black hole? Already I told. Okay, so any packet coming from here, any type of packet, data packet or control packet, no problem. Any packet which is coming here. Okay, suppose this is a malicious node. If any packet coming here, okay, control packet or data packet. Okay, so control packet means there are four control packet available: DIS, DAO. Okay, you can see it in the report. There are four packets available. Now, any packet comes here. Okay, it will simply drop. It will not forward. Okay, this is called black hole attack. But in the selective forwarding attack, what we are going to do means we are going to allow only selected packets. Okay, selected packets only we are going to send. Okay, for example, I can drop only the data packets I can drop. I can, okay, drop only the data packets. Control packets I can allow. Or control packets I can drop, only the data packets I can allow. Okay, anything. So if you are not allowing, if you drop everything, it is called black hole attack. But you are going to selectively, you are going to allow, or selectively you are going to drop. So you can drop only the control packets, or you can drop only the data packets. Okay, so this is called the selective forwarding attack. Okay, now how you can find? How you can find a packet is a control packet or a data packet? Okay, now if you take a packet, okay, a packet is coming. In the packet, there is a field available. The name of the field is called type. Okay, so type is the name of the field. Now, I'm going to check this, okay, type. If the type is equal to 155, okay, if it is 155, okay, this is the code number. It is a fixed one. If the type is 155 means, then I'm going to say it is a RPL control packet. Okay, if it is not 155, if it is some other number, okay, if it is some other number means, okay, it could be any number, okay, depending upon the protocol. It could be any number. If it is any other number, that is called, okay, that is called the data packet. Okay, that is called the data packet. So you must understand the difference. Okay, now we implement this. Okay, where we can implement means we can implement inside this, okay, folder. Okay, you can see Contiki core net IPv6 folder. We have UIP6.c. So this is the program already available. So this is for a sender node. Now in this program we are checking the condition if if type equal to, okay, type equal to 155 means it is going to be the control packet. So drop that packet. So we create another one. Okay, for example, selective forwarding control, sorry, data. So for data, we check if type is not equal to 155. Okay, type equal to 155 means it is selective forwarding control packet drop. Type not equal to 155 means selective forwarding data packets dropping. So this is the code we have inserted in this particular file. So this is about the implementation. So how we implemented this project. Okay. So mostly we have written the already programs available in the Contiki Cooja. So in that Cooja, we are going to change. We are changing the code. Okay. So this is what we have done. Okay. Now I'm going for the analysis part. So the analysis is a very important one. Okay. Now I'm going for the black hole attack. Okay. So what are the parameters we analyzed means the first one is the power consumption. PDR, packet delivery ratio, okay, ETX, okay, this is called transmission, okay, then duty cycle, delay, throughput, network conversion times, and control packets. Okay, you can see the control packets. These are the control packets. Okay, so four control packet DIO, DIS, DAO, DAO, acknowledge. You must know what is DIO stands for. Maybe the examiner will ask a question. Okay, now, so these are the parameters we checked for all the attacks. Okay, for all the attacks we have checked this. Okay, for example, I'm going for the control packets. So what is a control packet means? The control packet is, okay, the addition of four things. Okay, what I'm telling now, it is same for all the attack. Okay, but the first one who is explaining the black hole attack should explain very clearly. Okay, now, so control packet means it is addition of, okay, this is called sum. Okay, addition of DIO, DAS, and DAO. So the three things if you add, so that is called the control packet, the total control packets. So we run this simulation. Okay, we run the simulation for 30 minutes with the two scenarios, scenario 1 and scenario 2. There are two scenarios we have. In the first scenario, the attacker node is available inside the, okay, inside the what is it? Inside the radio range of the sync node. And here it is outside the radio range of the sync node. You can show your simulation also here. Okay, the black hole attack, you can show it here. Okay, you can just run the simulation and then you can do it here. Okay, now, so what is control packet? You are going to add all the three things: number of DIO packets, number of DIS packet, number of DAO packet. Now, if you see in the first scenario, we have this many numbers. Okay, so it's almost 2 lakh, okay, 4419 packets available, and here it is only 188 packets. So what it shows means if the attacker is available inside the sync node, okay, inside the radio range of the sync node, okay, if the attacker is available inside the radio range of the sync node, okay, the number of control packets is created more, which is not good for the network. So that means your network is not stable. Okay, whatever I'm telling now, okay, for black hole attack, the same thing for all that. So if more number of packets, control packets are generated means your network is not stable. Okay, the network is unstable. So in the second scenario we have 188 packets only. So this is regarding the convergence time. Okay, now I'll go for the second. The second parameter is network convergence time. Okay, network convergence time. So what is a network convergence time means how much time for a network it takes to settle. Okay, to settle. So initially your network will read, it will collect the data, it will learn. Okay, it will learn by itself. Then the network will become stable. So how much time it takes okay, for a network to be stable. Okay, that is very important. So this time should be less. If this time is less, then your network is good. If this time is more, then your network is not good. Okay, that means your network is having more disturbance. So now you see here, for the first scenario, okay, the time is 3225 seconds, 3025 seconds it is taking to settle. Okay, but in the second scenario only 295. Okay, based on this, okay, you see control packets, if control packet no becomes more, your network is not going to be stable. It is taking too much time for set. Okay, so this is what we understand here. So how we can calculate the network convergence time means this is the time of the first DAO packet, time of last DAO packet, DAO packet. Okay, the time sent, the first DAO packet, last DAO packet. So I'm going to minus this. If you minus this, then you can find what is the network convergence time. So for the first scenario, the network convergence time is 3525 seconds. Okay, seconds. Okay, that means huge. It takes a lot of time. But here it is taking only 295 seconds. Okay, this is what we have to understand. Then the next one is the throughput. Okay, what is the throughput means? How much of data sent in your network? Okay, that is bits per second. How many bits per second? Okay, that means the total number of bits per second. If you see, okay, how to calculate this means the throughput. Okay, you can see the number of packets, and this is the size of the packet. Then the last one is 8. Okay, multiplied by 8. Okay, why means I want to convert into bytes, then divided by, okay, the time, total time, how much of time you are running your simulation. Okay, that is 30 minutes. So total number of packets multiplied by the size of the packet, and then into multiplied by the 8 in order to take it as the bytes. Okay, and this is the last one divided by the total time. Okay, how many minutes or second you run the simulation. So for us it is 30 minutes. Okay, now if you see here, you can see 87,46406 bytes per second. Okay, because we multiplied by, sorry, bits per second, not it's bits. Okay, I want to convert into bits, so that's why I multiply by 8. Okay, it is in bytes, we are converting into bits. Okay, bits per second, so that's why we multiply by 8. Okay, the value will be in bytes, we are converting into bits, so we multiply by 8. So how many bits per second means 87,406 bits. Okay, in 1 second, okay, the data is sent in this S1 scenario. So here it is 26, okay, sorry, 2643. Okay, so 2643. So now you can understand. You see, in this second scenario, okay, so the throughput is less, but in the first scenario the throughput is more. Okay, that means your network becoming very disturbed here. Okay, this is the meaning. Then the next one is the delay. So what is the delay means? I'll show the delay now. See, this is the root, that means your sink. Okay, and then you can take any node. Okay, so now what is delay means? The time taken from, okay, from a node to the another node. Okay, I want to send a packet from here to here, so how much of time it is taking, okay, to reach means, okay, this is called delay. Now you see the second topology, it is 58 seconds is the delay. But in the first topology, sorry, scenario 1, it is 58 seconds. But here it is 12. Okay, so it is taking very less. So the delay should be less. If the delay is less, then your network will be good. Okay, the network is good. So this is the meaning, delay. Then the next one is the duty cycle. So what is duty cycle means? So this is related with the power. Okay, already we have power one here. I will explain what is this, the duty cycle. Now, listen duty cycle, transmit duty cycle. There are two things available. Okay, what is the listen duty cycle means? So a node is listening. Okay, for example, for every node, the node is listening for the data. Okay, the data to come. So for that we need some power. Okay, some electricity we need. Then the next one is a transmit duty cycle. So what is transmit means? For sending the packets. So there are two things available. So you are waiting for receiving the data, that is called listen. and then you are going to transmit the data every node. Okay, so how much of power used for listening? Okay, how much of power electricity used only for listening, how much of power used for the transmitting the data. Okay, this is we are calculating. Okay, now how to calculate? This is the formula. So what is this rx cpu lpu? Okay, I'm coming here. Okay, you can find it here. So using this formula we are calculating. Okay, so what is the power means? You see, for listening it took 162.5 percentage of power for listening. For transmitting, 828 percentage of power. So that means here more packets are transmitted. Okay, we already saw. Okay, you see control packets too much. So we actually this should be equal. Okay, it should be equal. Listen duty cycle and transmit duty cycle should be equal. Okay, 50%, 50%, 60%, 60%, 70%, 70%. It should be like that. But here what is happening? For a transmit, it takes more power than the listen. But if you see the second scenario, here it is almost the same. 120, 113. It is almost the same. Okay, for the transmit power and also the listen power is almost the same. So it is not taking too much time for listen or okay, transmit. Almost it is equal. Okay, so this is the duty cycle. Then the next one is called the etx. So what is etx means? It is called the extend, or we can say it is a transmission. Okay, E stands for extend transmission. Okay, that means jump. You might have already studied this in some networking courses. Okay, you see what is ETX means. I'll just show it. So this is your network now. So this node wants to go to the root. Okay, that means the sink. So what is the ETX means? 1 and 2. This is ETX jump. How many jumps it is making? Okay, that is called the ETX. Now, so the ETX, okay, suppose if there is any attack, means the ETX will be more. Okay, for example, this is a malicious node means, so this person cannot reach, okay, very easily. So this person will go some other node, then it will send it to the sink. So ETX is the number of jumps taken, okay, to reach the sink node. Okay, here you can see, so here it is going to be 20 and this is 19. Okay, so if ETX is less, your network is good. If ETX is more, you are making more jumps, okay, to reach the sink. That is the meaning. Okay, then the next one is a PDR, packet delivery ratio or packet delivery rate. So what is this means? Number of packets sent, number of packets received. Okay, for example, you see this node, I'm taking this node. So this node sent 100 packets, okay, to the sink. Okay, it's in 100 packets, but the sink received only 50 packets. Okay, sink received only 50 packets. What about the remaining 50 packet means? Maybe it dropped because of attack. So now what is the PDR means? The PDR is 50 divided by 100. So total number of packets received divided by total number of packets sent. Okay, into 100. So this is equal to, okay, 50%. So the PDR should be 100%. Okay, the PDR should be 100%. Then only it's a normal network. But if you have any attacks, the PDR will be very, very less. Okay, you see here, in the first scenario, the PDR is 94. It should be 100. Okay, but it is not 100, it is 94. In the second scenario, you see, okay, it is going to be very worst, 69 only. That means huge packet is lost here in the second scenario compared with first scenario. So 69% of the packets, okay, is received. The remaining almost 30% drop. And here it is almost 6% drop. Okay, this is called the PDR, packet delivery ratio. Now, I go for the CPU, sorry, power. Power consumption means the electricity consumption. This is very important in a wireless sensor network. So there are 4 different types of power available. Okay, so we calculated 4 different types of power. One is called the CPU power, then LPM power, listen and transmit power. So these are the 4 different types of power. So every power we calculated separately, and if you mix all the 4, okay, this is the formula. This formula is fixed. Okay, this formula is fixed for the type of device. Okay, so we use Sky. Okay, we use Sky mode. For a Sky mode, this is the formula we have to use, and we have to calculate the power by using this formula only. So CPU into 0.5, LPM into 0005. Okay, so transmission into 17.4, and then RX. RX means receive. This is transmit power, receive power. So this is the formula. So this formula we cannot change. Okay, it is for the Sky mode. So based on this formula, you can see the power consumption. So here the power consumption is 0.001438, and here, okay, here the power consumption is less. Okay, you can see the number of zeros. Three zeros available means here the power consumption is less, here the power consumption is more. Okay, so this is how we can do the analysis. So this is for the black hole attack. The same thing we have to go for the selective forwarding attack. Okay, now in the selective forwarding attack, so I just give you a summary, and I'm not going to tell everything. Already I explained everything. Okay, you see, CTO, control packets. So we are going to add 1, 2, 3. Number of DIO packets, number of DIS packets, number of DAO packets. So this is going to be the number. First scenario, second scenario. Then network convergence time means how much of time it takes, okay, the network to settle. Okay, so here 2557 seconds, it is only 44 seconds. Okay, if you observe all S1, that means scenario 1, it takes more network convergence, and also the control packets will be more. Then, so what is the throughput? Throughputs bits per second. Okay, so this is the total number of packets, TP, total number of packets into the size of the packet into 8. So divided by the time. Okay, so in 1 second, this many number of bits transmitted. Okay, 2147 bits in 1 second it is transmitting. Then, so what is the delay? Delay means time taken from one node to the another node, okay, to reach. So here, okay, you can see the 49 seconds and 44 seconds. Okay, this is the delay. Then duty cycle, there are two types available: listen duty cycle, transmit duty cycle. So how much of electricity we spend for listening, how much of electricity we spend for the transmit. So this is, okay, 134% of electricity it is spent for listening, 268 for transmitting the data. Okay, here 142% of electricity is used only for listening, and 387 is used only for transmitting the data. Then ETX means exchange transmission. So that means the number of jumps. Okay, number of jumps needed from the node to the sink. Okay, so this is 20 and 20. It is almost the same in this. Excuse me. So PDR, packet delivery ratio, how much is the loss? So 86% we received, remaining is a loss. Remaining 14% is a loss. So here 68% of the packet received, the remaining is loss. And then this is the power consumption. So power consumption can be calculated by using 4: CPU power, LPM power, listen power, transmit power. So using these 4, we calculated these values. So here, okay, it is 878, okay, 000 979. Okay, so this is how we can calculate that. For every attack, the value will be changed. Okay, now you can continue like this for all the attacks. Okay, now finally what we did means we are going to take all the attacks. Okay, you can see BHA, that means a black hole attack scenario 1. Okay, this is somebody should do this, present this. Okay, you can present for your attack, then somebody who is very strong, you can go for this. Okay, so this is for all the attacks. So now BHA means black hole attack scenario 1, scenario 2. Selective forwarding attack, okay, data, scenario 1, scenario 2. Selective forwarding attack, control packets, scenario 1, scenario 2. And this is flooding attack, scenario 1, scenario 2. DODAG attack, scenario 1, scenario 2. Okay, the next one is the decreased rank attack, scenario 1, scenario 2. So for all these attacks, we are taking the power, we are taking the PDR, packet delivery ratio, exchange transmission, listen duty cycle, transmit duty cycle, delay, throughput, network convergence time. So we bring it everything in a single table. okay, for doing the analysis. Okay, now we'll go one by one. So first we are going to analyze each and every parameter. Okay, for example, power, we are going to analyze it separate. PDR analyzing separately. Okay, each and everything we are going to analyze separate. So now I'm taking the power consumption. So if you see all the attacks, okay, BHA1, okay, that means black hole attack, okay, selective forwarding attack. So if you compare all the attack, so which attack consume more power means, okay, so FA, that means flooding attack scenario 1, okay, it consumes lot of power, okay. So BHA2, okay, black hole attack scenario 2, it is consuming less power. Okay, so black hole attack scenario 2 is consuming. Okay, if you explain the highest and the lowest, if you explain, it is enough. So the highest power consumption is, okay, flooding attack scenario 1. The lowest is black hole attack scenario 2. Okay, so this is what we identify. So what I'm concluding here, what is the conclusion here means, so that means the flooding attack, if the attack is available inside the sync node, it consumes lot of energy, okay, lot of power. Okay, this is the conclusion. Now I go for the ETX, okay, transmission, end to end transmission or exchange transmission, okay, anything, it is from one device to another device, how many jumps. So if you see the ETX, exchange transmission or end to end transmission, you can see here which is consuming, which is taking more time, okay, which is taking more time and which is taking less time, okay, the less number of jumps, okay, the less number of jumps which is taking, okay, this is called hop by hop. So which is taking the highest means, okay, you can see here, so the DODAG, okay, so if you want you can make the picture big, okay, so the DODAG, okay, I think DODAG or something else. Yeah, DODAG S2. Okay, it is taking the highest one. Then, so which is taking the least. So the less number of jumps means, okay, this is ETX 52. Is there anything? No, this is wrong, something wrong. No, the statement is not correct. The statement is not correct. Please check it in your PPT and correct it. So the highest is 27 is the highest. Then the least is, okay, 18.45. Okay, this is the list. So SFA control S1, it takes the least ETX. Then DODAG S2. Okay, it is taking more ETX. Okay, the line is not correct. Please check it in your PPT and change it. So like this, for every attack, so we are going to see which one is the less and which one is the more. Okay, so if you compare like this, it will be good. So now final conclusion. Okay, the final conclusion I'm going. So final conclusion we can see here. So power consumption, which attack is having high. Okay, so flooding attack S1, packet delivery ratio, selective forwarding attack control S2. So ETX decreased rank attack, listen duty cycle flooding attack, okay, transmit duty cycle flooding attack, delay selective forwarding attack, selective forwarding attack, selective forwarding attack. So what we are concluding here means, so the flooding attack and selective forwarding attack are very important attacks. So they are affecting our network very seriously. Okay, so we have to be very cautious with flooding attack and selective forwarding attack. So this is the final conclusion of this work. Okay, thank you. Hope you understand.